Welcome back to Chapter 7. In this chapter, we are going to be learning about linear regression. Last chapter, we were learning about scatter plots and correlation and association. Linear regression is where we put that line of best fit. So we're going to learn a bit about that. This is something that you have done since at least Algebra 2. So I know that you have experience finding lines of best fit. There will be more, however, in this we will go a lot further in depth, but the basics of finding a line of best fit are actually still the same. So let's take a look at our learning targets. We can use regression models to estimate values. We can answer conceptual and vocabulary questions involving linear regression. We'll be able to analyze and interpret residuals and residual plots. See, that whole residual word is a word that you probably didn't see in those other classes. Find and interpret the slope, intercept, or linear regression model. And find, interpret, and evaluate a correlation or squared correlation. So, our least square regression line. What is that? So the least square regression line, it's a line of best fit. However, it's a specific line of best fit because there's several different ways we could find lines of best fit. Like, how do you quantify best fit? Well, that's what the least square regression line does. It actually quantifies what the best fit is going to be. And so this would be a scatter plot that's a pretty strong linear relationship here, and we get the line of best fit. The line is going to have the equation y equals mx plus b, but we're not just going to have y. We're going to have this little symbol here. It's y with this little hat thing on top of it. In fact, this is called y hat, because in statistics we get to use fun variables like that. Generally speaking, the hat is going to mean a prediction. When we're dealing with probability, we'll have p hat. In fact, later on in this lesson, we're going to use an example where we're going to have speed as a response variable, and so we could write it as speed hat. So the hat just means that that's going to be our predicted value. So least square regression line is y hat equals mx plus b. I mean, that's just a general form of a line. We're going to get a bit more in depth on that in another slide or two. But we're looking at why they call this the least square regression line. So how we quantify it is we're going to look at the residuals. What are the residuals, you may have just asked yourself? The residuals are going to be the observed value minus the expected value, or y, which is the observed values. Those are all the little y values of all these little points, minus the expected value, which is the y value of the line. And so what that looks like is this. Each of these, so this is just an enlarged and simplified version of this graph, each of these is a residual. This one is going to be a positive residual because the y is bigger than the y hat. Notice the y hat is that predicted value, which is on the line. When we plug in the value of x, in this case 26, into the equation, that's what the equation gives us. The observed value is what the actual point was when x equals 26. And so that distance in between is the residual. So the one up here was positive. The ones below the line are going to be negative. And so we're going to use the residuals to get the least square regression line. So we still have that square word. Why would we use square in the name? Well, that's because we're going to find the average here. Now, if we just averaged all the residuals, we should get about 0, because the stuff above and the stuff below is going to balance each other out. However, we don't necessarily want 0. We want to know how far away are they. So a way to make them all positive is to square those values. So if we take those values squared, now we can add all of those up, and the least square line is the line that makes the sum of these squared values the smallest possible. So if we move the line just a little bit, those squared values are going to get just a little bit bigger. So that is why it's called a least square regression line. Sometimes it's abbreviated as LSRL for least square regression line. And we'll talk about how to find those in just a minute. So I had mentioned that we have y hat equals mx plus b as the general form of the line. That's not really how we look at it, though. We're going to look at it as y hat equals b naught, that's the little b0 thing, plus b1 x. When we are in more advanced mathematics, we tend not to do the y equals mx plus b or y equals ax squared plus bx plus c, things like that. We actually switch the order. So the constant is first. The constant will always have b naught, or sometimes a. And then the linear term would be next. Always has b1, or sometimes just b. The squared term would be next with b2. The cubed term would be b3. And so it's in order like that. So it doesn't matter how big of a polynomial we have, those values are always with the same. And so b naught would always be the constant. b1 is always the linear coefficient. b2 is always the quadratic coefficient. And so we switch the order. This does not change. Like, this is no different than y equals mx plus b, except it's b plus mx. So how do we find the y-intercept and the slope? Well, there's a formula for each of them. The slope formula, b1 is going to be r, that's the correlation, times the standard deviation of y's divided by the standard deviation of x's. Slope is change of y over change of x. So we have y over x, we have standard deviation of y or standard deviation of x. And then the correlation gives it's a multiplier, and it also gives it the sign, because the standard deviations are both going to be positive. So the correlation gives it the sign. That's why when it's a positive association, it has a positive correlation, and the same with negative. So that's the slope. And what the slope does is it gives us the average change of y for every one change of x. The y-intercept is going to be b naught. So the y-intercept is going to be y bar. That's the mean of the y values. So I know that these values, they're all ordered pairs. It's x comma y, x comma y, x comma y. If you took the mean of all the y values, you get y bar minus the slope times the mean of all the x values. So notice this looks kind of like the equation of a line. What this means is that the least square regression line will always go through x bar comma y bar. Always, that will be a point on the line. But that's how we can find the y-intercept. So when would you be using these equations? Not very often. And these equations are also on the formula sheet. On the AP test, you get a formula sheet. You get it on everything that we could possibly do in class as well. Generally speaking, I give it to you on day 1 of class. I didn't this year because you have like your books and stuff like that. Like, you don't need a formula sheet. I will post it for you, however, so that you can have it and use it. But these are both on the formula sheet, so you do not need to memorize these. And generally speaking, you do not need to use these. We will usually use technology, calculator, StatCrunch, Desmos. The Desmos application for regression is really kind of slick. But we'll use something like that to find the equation of these best fit lines. When would you possibly need these equations? Like, how could I give you a problem that forces you to use these equations? And would I do such a thing? The answer to that is yes, of course I would do such a thing. And generally speaking, you're going to have a question like that on the AP test as well. It's like just a multiple choice question. So it's not a big points type thing, but if you want all the points you can get, you want to save the ones that you miss for the hard ones. This one wouldn't really be a hard one. It's just a couple formulas. So how would we do this? Or how would I do it? I would just give you some information. I wouldn't give you the data. I would just give you the means, the standard deviations, and the correlation. And then from here, you just need to plug them into the equation. So the slope, B1, is going to be the correlation, 0.81, times S of y, which is 8.6, over S of x, 18.8. And we can do the calculations here using a calculator, obviously, to get 0.37. And what it is, so we have our S of y units, mile per hour, over the S of x units, feet. And so what this data was from the speed of roller coasters at it given a certain height. How much speed will they get to? And so this says that on average, that's important, on average, or predicted, on average, for every 1 foot we increase in height, we're going to gain an extra 0.37 miles per hour of speed at the bottom. So that's what that slope means in context. And then B naught, our y-intercept, is going to be y bar, which is 37.7, minus B1, which is 0.37, times x bar, which is 59.3. And so B naught, if we do those quick little calculations, we get 15.8 miles per hour. And so what this is if we are at 0 feet up, the roller coaster is going to be going 15.8 miles per hour. Now, if we just started a roller coaster at 0 and said go, it's not going to be going 15.8 miles per hour. The y-intercept will sometimes have an actual meaning. Sometimes the y-intercept won't have any meaning at all. Knowing what something's going to be when x equals 0 is not always useful information, partly because sometimes x just doesn't equal 0. Like, it doesn't make sense in the problem. Like, for instance, if we were looking at a graph with height versus shoe size, if shoe size was on the x-axis, your shoe size is not going to be 0. Like, that's not an option. So having that be 0 doesn't make sense. And then other times, like in this situation, I bet once we get away from the data that we were looking at, when we get closer to 0, I bet the graph's going to change. It's not probably going to be very linear all the way down there. So, but we do have our y-intercept. It is important for the graph because it gives us our starting point so we can sketch the line. Now we just need to plug it in. So y hat equals b naught, which is 15.8, plus the slope, 0.37 x. If we wanted to make a prediction, Like if we wanted to predict what is the speed when the height is 70 feet, we would just plug 70 in for x and find the y hat. That's how to make a prediction with our regression model. So that's how to find it by hand. I'll show you how to find it using technology in our class. You've done it using the calculators, so that's pretty easy. I mean, you go into stat, you enter your data, you go back into stat, you calculate lin reg, and stat crunch is actually remarkably easy. You can probably figure out where it is. I mean, you go into the things under calculate, you're going to have a regression option. You're going to choose linear. Um, but I'll show you how to do that at that point in time. Desmos, you type it in and I kind of like Desmos with it. You can actually see the model forming as you enter your data points. It's really quite beautiful. Residuals. Oh, I forgot to fade that in. So this down here is called the standard error. We'll see what that actually means. But we've already talked about residuals a little bit. Residuals, which is the error, that's where that little e is. Error is y minus y hat. It's the observed minus the predicted. So we want to make those as small as possible to get the line of best fit, but we also can use residuals for other reasons. One of them is we can make a residual plot. Why would we want to make a residual plot? A residual plot just graphs residuals. It basically flattens our line of best fit to make it the x-axis, and then we're just looking at the residuals. And what that does is it makes it so that the y-axis can be, like, it's more zoomed in, because the residuals aren't going to be as big as the entirety of our y values. So it allows us to see how good of a fit the line of best fit actually is. What we're looking for is a super, super boring graph. That's what we're looking for. So the line of best fit would be where the residual is 0. So it's just that axis. And we're looking for the points to just kind of be scattered about that axis. Like, they're not all going to be on it because the data is never perfect. We just want a general scattering. We don't want any kind of pattern because that means that they're not evenly distributed about the line. So something like this is good. Something like this isn't really good. We have this pattern here, which tells me that this line or this data was probably not particularly linear. We had the prediction was above it, and then it was below it, and then it was above it again. Tells me the data was probably looking kind of like this, so that when we made the line of best fit, it went like that. Now, that might be visible on the graph itself, or it might be really hard to see. Notice the residuals here are all from basically between -3 and +3. If our y values are going from like 0 to 300, we're not going to see that little -3 to +3. Those values are going to be really close to that line of best fit, and it'll look pretty linear. But again, when you get that zoomed in, you get to see a better picture of how that line is fitting. Notice last week we looked at the data and to make the scatter plot, and I added a line to it just to see kind of how close it fit, to see if it was linear-ish, and it looked like it had a little bit of a curve to it. this is what the residual plot would look like. On a residual plot, by the way, the x value, the x-axis, those are the same x-axes. So we're not, like, the x values don't change. The only thing changes is instead of graphing the observed y value, we graph the residual y value. So a pattern like this isn't good when we're looking at a residual plot. Also not good is something like this, where the residuals are getting further and further away. That makes it so it's not particularly linear. The regression line is not going to be particularly accurate because the error keeps getting bigger and bigger. Remember, as we are looking at our scatter plots and stuff, we're looking for a few conditions. The quantitative variable condition, well, it has to be that to do any of this stuff. The straight enough condition, this would kind of violate the straight enough condition. Also, the outlier condition, like we start having things that look like outliers there towards the end. There's another one that is the equal variance or something like that condition, where it stays basically the same. We have the same scatter about the line from beginning to end. Now, is it going to always be perfect, kind of like that first one? No. We might have some where it kind of bumps out or bumps in, but this one, like, it's really kind of flaring. It's kind of making a like a trumpet bell horn. I think it's a bell. Yeah, it's making one of those shapes. R squared. Oh, I didn't fade that in at all. I'm slipping. R squared. So R squared, first of all, it's the correlation squared. That's all it is. Secondly, it's the fraction of the variability that can be explained by the model. So what happens, sometimes we get the correlation. It says R equals 0.9. Okay, R squared is literally 0.9 squared, which is 0.81. Sometimes it'll give you R squared. Let's go 0.64. I'm using easy values here so that I can just do them in my head. It gives you R squared, and it asks for the correlation, 0.8. Sometimes it'll give you these values, and it'll say what percent of the variability or what percent of the data can be explained by the line. This would be 81%, because it's just that value. That's one of those concept questions, and they will try to trick you on that. But it is literally just R squared. They talk a little bit more about it in the book and kind of where it comes from. It comes from the residuals, and it is actually connected a lot more to R, but it's well beyond the scope of the course how it's connected. You just need to know that it is actually just R squared. The proof for that is really quite phenomenal. And the line of best fit, we'll be talking about this a bit more right towards the end of the year, but the line of best fit is based on our sample. So if we had a different sample, it would change a little bit. And so that's what the R squared helps us with. And when it changes a little bit, the part of the line of best fit that's super important is the slope. If the y-intercept changes a little bit, it just kind of moves it just a little. But when the slope changes, that's what makes big problems later on. And um, with regression, so we have the equation of a line. Now we are predicting y from x. So in the one we had the speed. So we had speed hat, was, I can't remember the exact values, 15 plus point, it was like 15.8 or whatever, but it was plus 0.38 times the height. And so we plug in the different heights and we get the speeds. If we wanted it backwards, if we wanted to know, if we knew the speed, we wanted to know what the height was, we can't just find the inverse of this. It doesn't work out. This is specifically going from height to speed. If we wanted an equation to go from speed to height, we would need to do the regression with speed as our x value and height as the y value. It is not the same thing as if we subtracted the 15 and divided by 0.38. It's kind of weird that way, but the order really does matter for our regression. So you can't just flip it around. And the last thing, when we're looking at regression, we want to know, is it reasonable? It's always a good idea to ask if it's reasonable. First of all, does it make sense? If it doesn't make sense, you really want to take another look at it. See if your calculations are right. But it might be that it's perfectly correct and it doesn't make sense. You just have discovered a new association stuff that we just hadn't known about before. But a lot of times it's at least worth a second look. But the book talks a little bit more about that too. So again, make sure you're reading the book. I do not have time to go over every single thing. I mean, we're already at 27 minutes here. And there's a lot of other stuff. I try to cover the parts that are not quite so easily read. So keep reading your book. I will see you in class for some technological tips. But until then, keep working problems, keep asking questions, and as always, happy mathing.